All right, moving on with segment 2. Your valence electrons, we've talked about the main group elements, but with the transition metals, which are the elements that are in the shorter columns, groups 3 through 12, and then the two that are pulled out at the bottom, those really vary. You can't really tell how many valence electrons they have based on their location. We'll learn about those later. Typically they have 1 or 2 valence, but we will not be concerned with those right now. Group 18, we've discussed that group before. That group is called the noble gases. They're pretty unreactive. That's how we recognize those elements. And for all but helium, they have 8 valence electrons. Helium only has 2 total electrons, so it can't actually have 8, but the rest of them do. When atoms react or bond or switch their electrons around, really the reason that that's done is to increase stability. And there are 3 kind of hallmarks for stability. One is that 8 outer electrons, which is called an octet, oct being the prefix that means the number 8. And then the other 2 have to do with what are called subshells. We haven't really discussed that yet, but within those different layers of electrons, there are also like subgroups of electrons that are grouped together. And those are called subshells. So for a subshell that has exactly halfway been filled or one that is completely filled, those are also stable configurations. So if a subshell is not exactly halfway or completely filled, that would not be considered stable. We are going to work on what you're going to learn in this segment and continuing on into the next couple segments. We'll be learning how to do what are called electron configurations. We are going to do predicted configurations, but understand that we're moving toward the fact that after we predict where those electrons are going to go, we are going to make some adjustments to create more stable arrangements for the electrons. But we'll begin with some pretty basic examples. So we'll turn to the back of the page. Now you're going to notice something that looks, I guess, probably pretty different from anything that we've done before. You're going to see some boxes, and then I've numbered those boxes. All right, and so each one of those numbers corresponds with an example that we're going to work. So for example number 1, we're going to start with a very simple one. So if you want to write the symbol next to number 1, this kind of looks like your paper, Li, we're going to do lithium. And if you locate lithium on your periodic table, you're going to see that lithium is element number 3. And just to remind you, that means that lithium has 3 electrons. Now these boxes represent the different, the numbers are the energy levels. So this 1 here represents first energy level, then the 2s are second energy level. And notice that the 2 is divided into 2 sections. We have a 2, and that's a letter S. And then we have a 2, and that's a letter P. And then it moves to 3. So in the second energy level, these are what are referred to as the subshells. So there's an S subshell and a P. The P is actually larger. Each one of these boxes can hold 2 electrons. So any S subshell, notice in the first energy level, the second, the third, the fourth, there are all, each one of those has an S sublevel, but every single time the S sublevel is only able to hold 2 electrons. The same pattern will happen with your P subshells. No matter what energy level you're in, those will always hold up to 6 electrons. They have 3 boxes, each one holding 2 electrons. D are going to hold 5. And that's as far as we're going to go for now for our beginning activity. There is a 4th sub-level that we'll talk about, subshell that we'll talk about later. All right, we're always going to fill our boxes, starting with the 1s and then proceeding to the right. And we're going to represent our electrons with arrows. Now, I typically draw half arrows like this. But if you're, sorry about that, and you're more than welcome to draw a regular arrow like that. There's no magic to it being a half arrow. It's just quicker for me to draw. So a full arrow is fine. In the boxes, we're going to, like I said, in each box, we're going to put 2 electrons or up to 2 electrons in each one. And they spin, when they're in the same subshell, they spin in opposite directions when they're paired up. So that's why one of our arrows will be facing up and one down. It really does not matter which one you put up or down. I typically, just out of habit, draw my first one up and my second one down. But if you want to draw them the opposite way, that will also be correct. So we have a total of 3 electrons. So this box I can hold 2. So I indicate that with an up arrow and a down arrow. That's 2 of my electrons. And I have a third electron. It goes here. So I don't have 2 electrons to put in this box, and that's fine. I've got lots of empty space. That's no big deal. So I've placed my 3 electrons. I'm finished. All right, so that is what's called an arrow diagram for this particular element. Let's look at oxygen. Okay, so number 2, we're going to do oxygen. So if you want to make a note of that and write the letter O there so that you'll know which element you did. And oxygen, when I locate that on the periodic table, I see that it is element number 8. So that means I'm going to fill up the boxes until I have a total of 8 arrows, because each of the arrows represents an electron. Okay, so I'll fill this one. That's 2. I'll fill the 2s. That's another 2. And I still have 4 electrons left because I've just placed 4. Now the way electrons fill in the P, it's kind of like on the bus where people don't really like to sit next to each other unless they're forced to. And the electrons do the same thing. They spread out until they're forced to pair up. So the first 3 of our 4 remaining electrons will fill separate boxes, but then we have 1 additional one, so we'll go ahead and pair this first one back up. So this is a total of 8. So anytime you have a subshell like this, you spread them out first, and then you go back and pair up.